Hey everybody, in this video we're going to learn about linear equations and also linear inequalities, and we're going to just work on solving them in various ways and take a look at a few examples. So let's just jump right into it. We're going to be working with equations in one variable, so basically we're going to see like just one letter. I'll stick with x most of the time, and let's just see how we would solve one of these types of equations. So for example, let's say I had this equation right here. Alright, so we have our linear equation in one variable. Notice the only variable you do see around here is x. So the goal of this equation at the end, after we do a bunch of work, is to say x equals something. X equals some value, hopefully. We get a number out of this. And so we're going to work on getting x by itself, because if we can isolate x on one side of the equal sign, then we should get what it equals on the other side. Okay, so start by distributing any values like numbers out here that would multiply into a group. So these parentheses is a group of terms, so we're going to distribute that. And even over here where we have just a minus sign, there is a minus like invisible 1 here, so we will distribute that as well. So we'll say minus 1 times x and minus 1 times 5. So that's going to be our first step to distribute. So we have our 10, and then this is going to be plus what becomes 6, 3 times 2x, and then we're going to get 3 times negative 4, so minus 12. And then over here we have 17, and that becomes a minus 1x, or minus x, and then distribute that to 5, and then minus 5. Alright, let's put some numbers together everywhere we can. So notice that we have constants on the left side that can combine. 10 minus 12 is negative 2, so 6x minus 2 when we put those together. And then over here 17 and minus 5, so we get that that's going to be negative x, and then that's a positive 12. Okay, and you could have said 12 minus x, and that's the same thing. So now here's where you make a choice. You do want to get x by itself on one side of the equal sign, so you can either bring your x's to the left or to the right. Either way you will get the correct answer. Just depends on your choice. So you're going to say, maybe this time I'm going to go to the left, so I'm going to add x to both sides of my equal sign. So notice the x's are gone on the right side, leaving you with just your number 12, and on the left side you now have a total of 7 x's. So 7x minus 2, and then almost the last step, we're going to move this 2 over, so add 2 to both sides. And so we get 7x equals 14. And then you can see the last step we could do here is just get x by itself, which is to undo the fact that it's being multiplied by 7. So if it's being multiplied by 7, to undo that, we're going to divide by 7, giving us x equals 2. And so if I back up really quick, we could just show that we would get the same answer if I move the x's to the other side. So I'm going to just do this work in green. So if I move my x's at this step to the right side, then I would end up, and I'll move it over here on the left, over here with green. I would get negative 2 by itself on the left side of the equal sign. I would get a total of negative 7 x's on the right side, and the 12 that's still over there. And then I would move over the 12 because I would want to focus on getting x by itself. So I would move over the 12 by subtracting, and then I would end up with negative 14 equals negative 7x. And if you notice, if you divide that by negative 7, you're going to get exactly the same answer we got. Sorry, let's fix this. These are all supposed to be a negative 7. We would get 2 for x. Okay, so we did it 2 different ways. We got 2 both times, but the nice thing is that we can actually check our work on our linear functions. So I'm going to go back to the very beginning, and I'm just going to plug in our answer and see if it's equal on both sides. So we had x should be 2. If I plug it back in, then hopefully that works. And this equal sign in the middle here, this one right here in the middle, we want to make sure that this is validated. So 17 minus, we're going to plug in an x right there, and that was plus 5. Okay, so that's the really nice thing about our linear functions, we can go ahead and plug in our value and see if we're correct. So I'm going to put a 2 in here for x and a 2 in here for x and see if that equal sign is still true. Alright, so we have inside the grouping symbol, inside the parentheses, this becomes 4 minus 4. So that's just 0. So we have 3 times 0. And there was still a 10 plus this on the outside. So this whole left side of the equal sign becomes 10 because 3 times 0 is just 0. On the right side, in the parentheses or grouping symbol, we do that first. So that's 7. So that we have 17 minus 7. And then on the right side, that becomes 10. And 10 does equal 10. So we can say with confidence that the answer to this linear equation is in fact x equals to 2. Alright, let's take a look at another example. Now this one looks different. As you can see, it does have just our one variable x, but it does have fractions. And so when you have an equation where you have fractions, what could make your life easier in order to move forward with it is to multiply by the least common denominator. So the least common denominator, or LCD, is the denominator that each of the other denominators all multiply into. So if we have a 6 here and a 2 here, and technically there's like an invisible 1 here, so we don't even have to worry about that one. 2 and 6 both go into 6. They both multiply into 6. 6 times 1 is 6, and then 2 times 3 is 6. So what we're going to do is we're going to take this equation, and whatever we do to one side of the equal sign, we have to do to the other side. So we're going to multiply both sides of this equation by 6, the common denominator. And then when we multiply, be careful, don't just cross off the 6's like canceling. They will divide out right here, but you do have to distribute the 6 or the denominator to all of the terms. So we're going to distribute it first, then we'll do some canceling or dividing. So we have 6 times the first fraction, x plus 7 over 6, and then we have also the 6 times the second fraction. So that's the tricky part, where sometimes we might want to like divide it out or cross it off, but it's not actually gone until we do this division all the way through. So this over here is negative 24, and so now I can go ahead and cross some things off. 6 divided by 6 is 1. 6 divided by 2 is 3. So I don't really have to put the 1 here. I could just sort of leave that off, but if you want, there's an invisible 1 right there. But I definitely have to put the 3 because it's a number that's going to change this 2x minus 8. So now if I keep simplifying, I have x plus 7, and then over here we're going to have 3 times 2x, which would be 6x. And then also that 3 is going to distribute, because it was outside of the parenthesis here, to the 8. So that becomes a 3 times negative 8, so minus 24. And then notice what happens when you multiply the whole equation by the LCD. There's no more fractions. So as soon as you do that and distribute, after we simplify, fractions are gone. So that's what I was mentioning about making the rest of this process easier if we just make the choice to multiply the whole equation by the LCD. So we've done that. Now this is a lot simpler than it was to start with. Let's combine some like terms. We have a total of 7 x's, and then as far as our constants go, 7 minus 24 is negative 17, and then on the right side we still have negative 24, and then just a couple more steps. We're trying to get x by itself, so let's move over this 17 to the other side of the equal sign, and then we'll have one last step and get x. So we have 7x is equal to negative 7, and last we're just going to divide by 7 on both sides, and notice that we just get x is equal to negative 7 divided by 7, so x equals negative 1. And then remember, we can always check, so that's the really nice thing about these equations. With our math, we can check if we are correct. So going back to the beginning, we can plug in a negative 1 right here and see if it's equal. So I'll just do that off to the side real quick. So where there's pink, I'll say that that becomes a negative 1. So negative 1 plus 7 over 6. And then we have 2 times negative 1, so that will become a negative 2 minus 8 over 2. The whole thing should equal what it equaled before, negative 4. Let's verify. So this becomes 6 over 6, and this one becomes negative 10 over 2. And so that's just going to give us 1 minus 10 over 2 is 5. So 1 minus 5 is definitely negative 4, which is what it was to start with. So there's another example. If you have fractions, you can nicely get rid of them by multiplying by the least common denominator. Okay, let's try one more, and that has this format now where we have decimals. So this is actually really similar to the last one, where we can make this easier on ourselves if we don't have to deal with the way that this looks right now in terms of decimals. So what you can do is you can look around at the decimals and see what place value the decimals are in. So like this one is 0.06. The 6 is in the hundredths place. Over here the 9 is in the hundredths place. And then over here the 7 is in the tenths place. So similar to LCD, what you're going to multiply by here is what place value you're in. So the furthest in. So the 7 is in the tenths, but the other two are in the hundredths. So what we're going to do is we're going to multiply both sides of this equation by 100, and then that way we're actually going to be able to get rid of the decimals, and then that'll be a lot easier to work with. So we're going to distribute first, and then we'll start simplifying. So we'll distribute over here, here, and then over here. And so what we have on the left, and we'll just write it out for the first one, but it's going to basically make the decimals go away, because if you have 0.06 and 6 is in the hundredths place, well, if you multiply by 100, then it's no longer going to be a decimal. If you work this out, you just get 6. You'll get 6.00, or just 6. And so over here we're going to get 6 times x, and then similarly in the middle here we're going to get 9 instead of 0.09. So 9 times 15 minus x once we multiply by 100. And then on the right side, that was 0.7, and so that's in the tenths place. When we multiply by 100, if you want to, you can work that out, but what's going to happen is it's going to be 70.0, or 70. So that one's going to be 70 times 15. But notice at this moment all of the decimals are gone, so that's really nice. So we were able to simplify the way that this looks, and now we can continue on and solve this and not have to work with the decimal values anymore. And so we multiply by essentially the furthest place value that we saw in the equation, and that was the hundredths place. So we multiply by 100. So we have 6x, and then that becomes 135 minus 9, don't forget to distribute, minus 9x, and then over here we're going to get 1050. And then if we combine our x's, we have negative 3 on the left side. And let's go ahead and move over this 135 at this moment as well. So if we subtract 135 from both sides, we're going to get that this equals 915. And then last step, divide by negative 3. And so we get that x is equal to negative 305. And so we could check and plug that in, and we'll see that that one actually does work out as well. So just to generalize, the outcomes that you will get with these linear equations is basically one of three things. So you'll either get one solution, which is actually what we were getting for each of the examples that I showed you, or you might get that there's no solution, and this is valid. This does occur sometimes. And then the third possibility is that you actually get that there are infinitely many solutions. Alright, so the way that these will look, as you could see from the examples we did, you get one solution when you are able to work on solving, and you actually get that your variable equals a number. So that would be one solution. You would get no solution if you go to work out your equation and you do some work, and at the end you get that your variable is gone, like it disappeared. And that might be something like maybe you got 3 equals to 7 and your x is just completely gone. So you basically get something false. Your variable disappeared through the work and you get a false statement. And so that would be no solution. And then infinitely many solutions is if you work out solving your equation and then you get something where x or your variable disappears, but you get a true statement, maybe like 3 equals 3. So if you get a true statement and you aren't actually able to solve for your variable like that we did and get a number, x equals, but you get something true, then that's actually infinitely many solutions. Visually, if you were to graph equations, 2 equations, like let's say one represents the left side of your equal sign and one represents the right side of the equal sign like we were solving earlier, it would be one solution if you graphed the 2 equations and they intersect at a single point. You would get no solution if you were to graph the 2 equations or 2 sides of the equal sign, and when you went to graph them they never intersected, and that would be because they're parallel. And then the infinitely many solutions would be if you were to graph the 2 equations, when you graph them they're actually right on top of each other. They end up simplifying to become the same equation. So that's the possibilities that you'll get when you're doing these linear equations. So the other thing we want to discuss now is actually linear inequalities. So this one has a little bit more involved with it because it's not just equal signs, and so we have to keep track of our symbols, whether we have less than or greater than, or less than or equal to, or greater than or equal to. And there's one extra piece of work we have to do with these ones, and it's basically this one here. So if you multiply or divide by a negative number, then we have to flip the inequality symbol, because it's changing the values and the direction that the symbol should be. And we'll take a look at this when we do an example, but this is the extra thing that we have to do that we didn't have to consider when we were just solving equations. Okay, so we're going to start with this example. So we have this inequality here. Notice that our symbol is an inequality symbol, not an equal sign. It does have the equal bar underneath, so this one is saying the left side is less than or equal to the right side. Our goal is still the same. We want to get x by itself, and so let's work on that and then see what happens. So we have 3x. If we distribute -2, we're going to get minus 4x, and then distribute it over here and get minus 8. And then the right side hasn't changed yet. We're going to combine our like terms on the left, and we get negative x minus 8, and the right side again still hasn't changed. And then now let's decide which way we want to put x. It doesn't matter which way you choose. You could just make a decision on left or right. I'm going to go ahead and go left. So if I move my x's to the left, notice so far I haven't multiplied or divided by anything negative. So we just have negative 3x, and I'm going to go ahead and move over the 8 at the same time. So let's say plus 8 over here, and so we have that negative 3x is less than or equal to 9. And now remember, the goal is to get x by itself, and here is a moment where we have to pay attention. Right here at this moment, this is where a little alarm goes off and says, hey, remember, if you ever multiply or divide by a negative, you have to flip the symbol. And so I'm doing that at this moment. I'm dividing both sides by a negative number. And then we're going to say this is positive x. This becomes -3. 9 divided by -3 is -3. And then the symbol right here is going to flip direction. And it's because what was -3 times x was smaller initially, but when we divided out the negative, then that side became bigger. And so now x is greater than or equal to -3. And this is the solution. It is a set of values. It's not just a single value, because it's saying any number -3 or more will satisfy this inequality. And so on a number line, you could say that -3, let's say, is right here. Our solution says that any x greater than or equal to -3, so any x over here, satisfies our inequality. And we could check it, like let's just pick something over here. Let's pick 0. If we plug in 0 for x, so if this becomes a 0, and this becomes a 0, and this becomes a 0, well, based on our solution, the answer should work. It should be valid. So let's check just with that one choice. So we would get 3 times 0 minus 2. Okay, so I'm just going to write my work right underneath the original. So that would be minus 2. And then 0 plus 4, so that would be 4. And on this side, that would be 0 plus 1, so that would be 1. We would have -8 on the left side, and the right side is 1. -8 is, in fact, less than or equal to 1. So yeah, it's true. So any number we pick, -3 or more, would be a solution to this inequality. So you can write your solution set. So the solution set like this, you can write it as a set, the set of all x's, such that x is greater than or equal to -3. You can write it as an interval. You can say that we would start at -3 and want any numbers bigger all the way to infinity. And now you use parentheses when you use interval notation like this. When you use interval notation, we use parentheses and brackets for different situations. Brackets are used when you're allowed to equal the endpoints. So notice we could equal the -3 because this is greater than or equal to. And then we use parentheses when we can't actually include those endpoint values, when we can't equal them. And so these are different ways to write the solution set to this inequality. Now I want to show you visually as a graph what this could look like if we were to graph the solution set. Okay, so now let's take a look at what this would be as a graph. So we already solved it algebraically. We know the solution set is any numbers -3 or more. But if we go back a few steps and we recognize, okay, we simplified this to be -x minus 8 on the left side and 2x plus 1 on the right side. Well, these are both linear equations if we just took each side on its own. So let's say the left side is y1, so we could say the right side is y2. And both of these would be lines. And what we want to know is where they overlap, basically. So recall what we know about lines. We know that a line has the slope-intercept form of y equals mx plus b. So our slope on the first, or left side, the first line, would be this negative in front of x. So this one has a slope of -1. And then our y-intercept would be the -8. So our y-intercept on this one is 0, -8. So if we go down here, 1, 2, 3, 4, 5, 6, 7, 8, and then we go -1 for the slope, so down 1 and then 1 to the right, and then it would down 1 and 1 to the right. So that would be the left side of the equation. And now the right side, similar, we're going to say the slope is 2, and this time the y-intercept is 1. So that one we have 0, 1, and we're going to go up 2 and run 1, up 2 and run 1. So we're basically saying, when is the left side less than the right side, less than or equal to the right side? Because that's what this inequality setup is saying. So when is the green less than the blue? So notice that the green graph is underneath or lower than the blue, starting about right here. So if I kind of draw a line right there, if I look right here, after this point, moving to the right, green is now underneath the blue. So blue is above, Green is lower than blue, lower y values. And that's anything to the right of this point. And if you look at our labeling, it's a little hard to see, but that was when x was -3. So anything where x is -3 or more, anything to the right of that -3, our green graph is lower than or less than the blue graph. And so that would be another way to figure out this solution set visually. Okay, let's take a look at one last example. This is called a compound inequality, and that's because it's made up of two separate inequalities. And sometimes they're connected with the word and. Other times you can just put them together, or they're already together to begin with. And if you take a look, in both cases we have 2x plus 1 and then something about it. So we have that 2x plus 1 in the first inequality, it's greater than or equal to -3. So we could say that the 2x plus 1 is greater than or equal to -3. And in the second inequality, we know that it's less than 2. So we can write it as one big compound inequality and then work on solving it all at once, still focusing on getting x by itself. But now this time, we're going to work on all three sides of this at the same time. So we subtract 1 from all three parts, and we get -4 is less than or equal to 2x, which is less than 1. And then if we divide everything by 2, then we'll have our solution set. So we have that -2 is less than or equal to x, which is less than 1/2. And so this is the solution set to this compound inequality. And in interval notation, we would say that any number between -2 and 1/2 would satisfy this inequality. And notice we have an equal bar on -2, so we'll use a bracket on that side, and no equal bar on the 1/2, so we'll just use a parenthesis on that side, and that would be our solution. Alright, that's it for this one. Thanks for watching.